SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, this will be lecture number 20, mechanical measurements. The topic we are discussing is pressure measurement. We have already covered the basic aspects of manometry, that is using either a U tube or a well type manometer for making the measurement of pressure. So, what we will do in this lecture, to start with, we will take a simple example of a well type manometer with an inclined tube and see how we can calculate the pressure given the various input data for the problem. And then we will also look at how to calculate the error in the measured value of pressure by a simple analysis, which is based on the error propagation formula, which has already been covered in an earlier lecture. After doing that, we will look at several different types of pressure measuring instruments. To start with, we will look at the Borden gauge, and then we will also look at what is called a dead weight tester, which is used basically for calibrating pressure gauges or comparing different pressure gauges in order to ascertain whether the gauge is properly calibrated or not. And then we will continue our discussion on various types of pressure gauges, which are based on some advanced sensors, and specifically, for example, we look at gauges which depend on the displacement or the bending of a diaphragm, and the diaphragm movement itself is sensed by a transducer which is going to respond to the displacement. So, displacement transducers of different types are used, and we will see how they work and also how they can be analyzed from the point of view of understanding the working principle of these. So, to start with, let me just move on to the example 21, which basically is a problem based on what we have covered in the earlier class, the last lecture. So, we are given an inclined tube manometer and the fluid is water at 20 degrees Celsius, that is the manometer fluid, and the pressure to be measured is that of air, and the angle of the inclination of the tube is 20 degrees. If you remember theta, the angle. The well is a cylinder of diameter 5 centimeters or 0.05 meters, and the tube itself is of 1 millimeter diameter. The manometer reading is given in terms of the column length along the inclined tube, which is measured to be 150 millimeters, and we are asked to determine the differential pressure for the pressure of the air with respect to the atmosphere in millimeters of water and also pascals. We also would like to find out what is the error in percent if the density of air is neglected, because if you remember in the last lecture we talked about the fact that the density of the manometric fluid and the density of the fluid in which the pressure is being measured, both are going to play a role, and in many applications we could in fact neglect the density of the fluid in which the pressure is measured. Specifically in the case of mercury and air, for example, the mercury density is so large compared to that of air that this neglect may be justified. But if it is water and air, as we have taken up in this particular example, it may be a cause for a considerable amount of error. The second part of the question is to determine the error in the measured value of the pressure. If the manometer reading itself is subjected to some error of plus or minus 0.5 millimeters, while taking the reading we make that kind of an error, and also the density of water has an error of about 0.5%, because it is uncertain because of various reasons, especially the temperature measurement, or the temperature is given at 20 degrees. If the value of temperature has an error, the density will have a corresponding error, and so on. We will, for the second part of the problem, we will assume that all other parameters are subject to no error, and we will also neglect the air density in this part of the question, just to highlight some of the differences we find. So, what I will do is I will work out the solution on the board. In fact, I will go back to the, I will show you exactly what the data is. So, I have made a sketch for the example. So, we have the well on the left hand side, and the pressure to be measured is fed into the well, as you see here, and the density of the air is given as rho f, and the inclined tube is at an angle of 20 degrees as indicated here, and the distance between the datum and the reading which is taken in this particular case when the pressure is applied as P is given 150 plus or minus 0.5 millimeters. So, the angle is 20 degrees, and you see the advantage of this measurement is that even though we are measuring a distance of 150 millimeters for the change in the level of the liquid in the tube, the actual height of the manometer is only this vertical distance between the datum and the meniscus level here. So, that in fact, if you remember or recall, in the last lecture we said that the inclined tube is like an inclined plane, and it is a simple machine, and it is going to give you a mechanical advantage. In this case, what it does is it is going to give you a larger difference in the level of the meniscus, which is measured along the length of the tube. Using this, I am going to calculate a smaller height, which is what we should have measured to start with. So, we are amplifying the length by the inclined tube, and that is the mechanical advantage we can think in terms of. So, with this basis, let us just make a calculation. So, we are given some of the things, the density of the manometer liquid, this is water at 20 degrees. So, we have to go to a handbook which gives the density of water, and I have taken the value as 997.6 kg per cubic meter. The air whose pressure is being measured, the density has to be calculated. For this, we will assume, because the pressure differential between the atmosphere and what is measured is related to, after all, that 150 millimeters, and the 150 millimeters is very small compared to 1 atmosphere. Therefore, we can assume that the air is essentially at 1 atmospheric pressure as far as the density calculation is concerned. Therefore, we will say that the pressure of air for calculating density is essentially 1 standard atmosphere. This is also equal to 1.013 into 10 to the power of 5 pascals. We also know the gas constant for air, assuming it is an ideal gas. So, we will say Rg, the gas constant, is 287 joules per kg Kelvin. And the temperature is the same as this temperature, because the air and water are at the same temperature. This is also the temperature of the air equal to 220 degrees Celsius. We have to add 273 to make it in Kelvin. So, this becomes 293 Kelvin. So, by using the equation of state, we can calculate rho R G times T is equal to P air. From this I can calculate rho of air or the fluid in which the measurement is being made equal to P by R G times T is 1.013 multiplied by 10 to the power of 5 divided by 287, that is R G, multiplied by 293. This comes out to, the density comes out to 1.205 kg per cubic meter. So, you see that we have the water density or rho m equal to 997.6 and the air density is 1.205, both in kilograms per cubic meter. So, even in this case you can see that the difference between the densities, this density is very much higher than this, and it will be only 1 part in 1000 roughly, or a little more than 1 part in 1000. So, in essence it may be all right to neglect this, but of course, we will take into account, then we will see what is going to be the error in that one. The second part of the calculation requires two things. One is the area ratio. If you remember, the area ratio comes because we assume that the fluid, manometric fluid is incompressible. Therefore, to determine how much is the change in the height of the liquid within the well itself, we have to use the area ratio. This is how it comes to the picture. This will be given by 1 millimeter diameter for the tube, and the diameter of the well is 55 centimeters. So, this will be proportional to the square of this, and this comes to 4 into 10 to the power of minus 4. There is no dimension because the ratio of two areas. And let us look at the appropriate equation in this case. So, the pressure difference, if you remember, this will be P minus P atmosphere. What we are measuring is the difference between the pressure of the air with respect to the atmosphere. This is also referred to as the gauge pressure. I am just trying to introduce some of the terminology using this particular example. I am measuring the gauge pressure. If I am interested only in the absolute pressure, P will be called the absolute pressure, the gauge pressure plus the atmospheric pressure will give you that. So, however, I am interested only in the gauge pressure in this particular case. This is given by rho m minus rho air or rho fluid in general, multiplied by the gravitational constant G, multiplied by the reading or multiplied by, there are two factors inside this. One is because of the height which is measured, which is actually r times sin theta. So, I will put the sin theta here, plus the depression of the level within the well, which is calculated based on the incompressibility assumption. Sin theta will not come there. Therefore, this will be simply the area ratio here. And let me just look at this formula again. If theta equal to 90 degrees, it corresponds to the vertical tube case 1 plus AR, and that is what we had in the case which we treated earlier. Therefore, in the case of theta, if theta equal to 90 degrees, the inclined tube manometer becomes a vertical tube manometer, and this will become sin 90 equal to 1 plus AR. Instead of that, I have got sin theta plus AR. So, all I have to do is to plug in the values. Rho m is determined 997.6 minus rho a is 1.205, G I am assuming 9.81, R is 150 millimeters. So, I will convert it to 0.15 meters. In this formula, everything should be in SI units, otherwise you will not get pascals. That is very important. Multiplied by sine of 20 degrees. Sine of 20 degrees happens to be 0.342. So, we can make a note here is that this is 0.342, which is the same as sine of 20 degrees, plus area ratio is 4 into 10 to the power of minus 4. Actually, you will notice one thing, because the well is very large diameter corresponding compared to the diameter of the tube, the area ratio is very small, and actually this is negligible compared to this. This is 4 units in the 4th decimal place. Therefore, we can say that this is quite negligible. So, the idea of taking an example is to indicate or to get a feel for the apparatus or the instrument and understand what are the significant things, what are the insignificant things in that particular example, find out what kind of approximation is valid, and in this case you can see that the area ratio being very small, in fact we can ignore it, and most of the time it is actually done that way. So, in other words, I can simply say that I can remove this AR from this formula inside, this can be ignored or cut this factor, so that you get GR sin theta into rho m minus rho a, and indeed if you ignore rho a also, it becomes simply rho m GR sin theta, and this value comes out to 502.06 pascals. So, this is the first part of the question, which says please find out what is the measured pressure from this calculation. Now, in this calculation we have taken into account rho a. Suppose I neglect rho a, so I will just give the value in the bracket, neglecting rho a, you will get a value of 502.662. So, you get 502.06 if you do not ignore the value of the density of air, and if you neglect it, you get 502.66. Actually, by neglecting the density of air, you are actually overestimating the pressure by a small amount. In this case, it will be about 0.6 pascal. So, the error, so I will write it here, error in neglecting is plus 0.6 pascals. Of course, you can represent it also as a percentage, and the percentage value. So, I will write it in the next sheet. So, the percent error when you ignore the density of the fluid is the difference between the two, which is first one is 502.06 minus 502.66 divided by 502.06 into 100 percentage, and this comes to minus 0.121%. So, you get a value of what minus 0.121%. This is quite negligible, negligibly small. The second part of the question concerns the analysis of errors. So, the next one is error analysis, which will actually complete the solution to the problem. This is actually part B. So, what are the errors due to? We know that the value of R which is measured. So, we have R is equal to 150 millimeters plus or minus 0.5 millimeters. This is one of the sources of the error. We are also given that the rho of m has a 5% error. So, I will write it as plus or minus 5% error. So, I will say delta rho m 5%, that means that plus or minus 5 by 100 into 997.6. Actually, the error which is specified here is quite artificial, just to indicate the way you do the error analysis. In actual practice, the error may be much smaller than this. It is just to get an idea of how sensitive it is. I have just deliberately taken a large error. In practice, the error is going to be much smaller than this. So, the point is, we go back to the formula which gives delta p or p minus p a. I am going to make the approximation that the density of air itself is neglected. So, it becomes simply, so I will say approximately rho m g r, and in fact, I can also ignore the area ratio there. If you want, you can take into account plus a r. This is approximately this one, and I will just call this as delta p as a symbol representing P minus P, or the gauge pressure is delta P. So, if you remember the error propagation formula, which was covered in a earlier lecture. So, what does it say? It says that we have certain error in this measurement, certain error in this measurement, and these two errors are going to propagate to this. So, the propagation is from the right hand side to the left hand side, and we are also given that the other quantities are all known without any error. That means that g and sin theta, there is no error, and therefore, we will ignore it. But in practice, sin theta or theta itself may be subject to some error, and in which case we have to take into account also the error in the value of theta, and hence sin theta. So, if you write the error propagation formula, delta p, which can be obtained by simply logarithmic differentiation, because this is in the form of a product of quantities. So, this becomes delta rho m by rho m whole squared plus delta r by r whole squared plus or minus of under square root. Because in this particular case, delta p is a function of product of g m and r. G and sin theta are not going to come into the picture, because they do not have any error assigned to them. Therefore, there are only two sources of error, error in rho m, error in r, and if I substitute these errors in terms of percentages, this whole thing can be written in terms of everything will be percentage. Delta p be by p percent plus or minus of this percent whole squared plus this percent whole squared. That is another way of writing it. So, we will mention that it can be all in percentages. Both the left hand side as well as the right hand side will be in percentages, and all I have to do is to, this is 5%, point 5.0 whole squared plus delta r by r is 0.5 millimeters divided by 150 into 100 whole square. Because the value was not given in percentage, I have calculated in percentage by taking 0.5 is the expected error, divided by 150 is the actual measured quantity, multiplied by 100 whole square, this gives you the value. So, the delta p, I will say, is percentage, this is the error in the percentage is plus or minus 0.601. I think I might have made a mistake earlier. Let me just go back. this is 0.5%. So, let me just correct it, not 5%. Actually, it is 0.5 by 100 into 9. So, the point I was making at that time was with respect to 0.5%. I should have said that 0.5% itself may be too big to expect in this particular case. Therefore, the pressure is subject to an error of 0.6% because of the two uncertainties in the density and the uncertainty in the measured value of R. Just you go back and calculate or you compare this error with what happened when you neglected the value of the density of air. The previously I had a 0.12%. If you go back, you will see. So, the percentage error between the two cases, this was 0.12 and 0.6, about 5-fold. This error is not negligible. So, as in the previous case, we said that the error due to the neglect of the density of air itself is very small, it can be neglected, but not this, because this is about 5 times that error. So, in this problem, what comes out through this, through the numbers, is that some errors may be neglected, some errors may not be neglected depending on the circumstance. So, we will go back to the and continue with our discussion on the other types of pressure gauges. So, the first type we are going to look at is called the Borden gauge. Let me just briefly explain the mechanism or the way it is going to function. I have taken a picture which was available on the net, and so I have presented it here. It is from the net in which this Praveen Verma has put this particular picture, and a few more interesting pictures are available there. If one would like to look at them, one can go to the website and look at them. This is typically the appearance of a Borden gauge. The Borden gauge essentially consists of, if you see here, we are able to recognize there is a tube in the form of a C. This is the tube, okay, and this is connected to some linkage here, and eventually it is connected to a needle or the pointer which is going to move over the scale. Let me just go to the next figure, which is somewhat more clear. What it consists of is the Borden tube, which is some kind of a flattened tube. You can see that here. It is flattened and the cross section is somewhat elliptical, and the inside is communicated to the inside of the tube, which is sealed. The sealed tube, we communicate the pressure to be measured, and of course, the outside the pressure is the atmospheric pressure, or in some cases the outside pressure may be a different pressure. We can use this for measuring the differential pressure or the gauge pressure. By now, you will realize what gauge pressure means. Essentially, it consists of this Borden tube, which is fixed at one end, and then it is connected to a linkage mechanism, and there is a, it is not very clear here, but in the next sketch I am going to make it more clear. It has got some arrangement by which it is going to move a rack against a pinion, and the pinion is connected to the shaft of this needle pointer, and there is a spring. So, the spring is going to resist the movement of the movement of the Borden tube. If you have a pressure difference between the inside of the Borden tube and the outside, the tube tends to open up. When it tends to open up, it tends to move the pointer, and the spring force is going to oppose this. So, under equilibrium, the needle will take such a position that the forces due to the torque on the needle pointer due to the force exerted by the Borden tube is exactly compensated by the spring. The spring is the restraining element, and the pointer is going to take a position which will correspond to a certain angle along this scale, and the angular position can be calibrated with respect to delta p. A very simple instrument, and as we have already made clear in the previous lecture, it can be used for various ranges, starting from even below atmosphere to above atmosphere to very large pressures, very small pressures. It covers, Bourdon cage covers a very large range of pressure measurement. So, let us look at the internal construction. The internal construction is very clear from this particular thing, this sketch. So, you have the fixed end of the tube, this end of the tube is fixed, and it is in the form of a C, as I said, and it is connected to an adjusting linkage. This adjustment is for adjusting the 0 position, and then it is connected to the rack arrangement, and the pinion is actually connected to the needle shaft, and you have the adjusting screw here and the pivot here, and it is very clear. So, the pressure is communicated through this tube to the inside, and the outside is the atmospheric pressure, or if you want to measure differential pressure, P1 inside, P2 outside. So, the difference in the pressure is what is going to be measured, and the mechanism of working has already been explained. So, with this background, let us look at, for example, if I were to look at the calibration of a pressure gauge of the type which is indicated here. So, what is calibration? Calibration is, in this case, the pointer is going to occupy an angular position, and each angular position corresponds to a certain pressure difference between the inside and the outside, and I would like to make a scale on this circumference of this circle, or indicating the position of the pointer, and corresponding position of the pointer, a pressure reading must be indicated. So, that is what we call as a calibration exercise. So, the calibration can be done by using what is called a dead weight tester. It is a very simple instrument. So, what we have in the dead weight tester is, we have a fluid, in this case oil, which is in this cylinder, and the oil can be pressurized by using a screw, as is shown here. This plunger is going to go in and out and increase or decrease the pressure, as the case may be, and there is a dead weight, and there is a piston which is on which the dead weight is placed. This whole thing is vertically oriented, and if you can realize the pressure of the oil here, if the dead weight is just floating, that is, if the oil pressure is such that the pressure exerted by the dead weight on the piston, which is simply given by the weight which is placed on the piston here, the dead weight, divided by the area of cross section of the piston, that is the pressure. So, the calibration is done by having a known weight and the known area of cross section of the piston, such that the pressure can be calculated directly as the weight divided by the area of the piston, as simple as that. And this pressure is acting on the oil, and there is a side tube through which it is communicated to the gauge under test, and the gauge will experience the same hydrostatic pressure. The fluid pressure, the oil pressure is communicated, whatever is experienced by the liquid here, which is the oil usually, is communicated to the gauge under test. Now, what I have to do is to use different weights and adjust the position of the screw such that the dead weight is going to just float. That means that it is going to be freely able to move in and out. It should not be restrained. In that case, the dead weight divided by the area of cross section of the piston gives you the pressure, which can be expressed in terms of the weight in newtons divided by area in square meters, that will be in pascals, and directly the position of the needle here will correspond to the same pressure. Okay? A very simple arrangement, very accurate arrangement. This is in fact considered as a primary standard for pressure calibration. A typical dead weight tester which is available in the market, this is from Australian manufacturing. You have the gauge under test which is indicated here, the weights are added here, and then the screw is actually this handle, and this is usually put on the table at the table top, and then you can see that it will also have an arrangement by which you can find out whether it is level and so on, leveling screws are there and so on. You can see that this is a dead weight tester which is commercially available and is used for calibration purpose. Now, let us look at the other ways of measuring pressure. So, I am going to go to the board and indicate some of the methods. So, other methods of measuring I will simply say other pressure gauges or transducers. Let me just look at the principle of operation of several different types of pressure gauges. One by one we are going to go. As I indicated earlier, we could have a diaphragm, type gauge, and what is the diaphragm type gauge? Suppose I have a diaphragm which is held fixed at the periphery. This is actually a circular plate of some small thickness. So, we will say that thickness T, and if I apply a uniform pressure P on this side and uniform pressure of P A on the other side. Okay. So, I have a circular plate or a diaphragm held fixed at the circumference. At the periphery it is held fixed, and now I am applying the uniform pressure on the one side and the atmospheric pressure, of course, which is uniform on the other side. So, the diaphragm is going to undergo, if the P is greater than P A, it is going to undergo a displacement like this. It is going to undergo, so a change in shape. It is going to open out like this. So, there is a, if you look at the, there is a displacement y at the center or any other place. I am just taking the center. To make the figure more clear, let me just indicate it here. So, I have the diaphragm which is fixed, and it is going to undergo a change in shape like this, a change in shape, and I have a displacement which is measured at the center. I will call it YC, and let us take this as radius A, and the material has got some mechanical properties which are going to be important. So, let me look at the mechanical properties. The Young's modulus, from strength of materials, you must be already knowing about this quantity. Young's modulus is going to play an important role. The Poisson ratio, nu is the Poisson's ratio, is also going to play a role in determining the displacement of the diaphragm, and the formula which describes this is given by YC is equal to delta P delta P is P minus P A, as we already have written down earlier. P A is the atmospheric pressure, P is the pressure which is being measured, P minus P A is delta P multiplied by 3 times delta P divided by 16 times the Young's modulus times cube of the thickness T cube multiplied by 4th power of radius a to the power of 4 multiplied by 1 minus the square of the Poisson's ratio. Poisson's ratio for metals, if we are using a metal diaphragm, either stainless steel or some other metal, it may be anywhere between 0.3 and 0.5. Okay. And the Young's modulus is known. A is the radius of the diaphragm and delta P. Therefore, you see that the displacement at the center, is proportional directly to delta P, and all the other things are constants, material constants or geometrical constants. Therefore, you can see that Y C is equal to some k times delta P, or you can also write it as delta P equal to Y C multiplied by k dash, where k dash will be nothing but 1 over k, and k dash is nothing but the gauge constant. Therefore, if you have a diaphragm, as is indicated here, and if you have a method of measuring the displacement at the center, of course, you can measure the displacement at some other location also. At the center it will be maximum, and therefore, presumably it will be more easy to measure the maximum than at some other location away from the maximum. So, if you are able to measure the displacement, you can relate it to the pressure by a simple linear relationship given by delta P equal to Y into k dash, where k dash is a constant which is once for all determined by 3 by 16 E T cube a to the power of 4 1 minus nu squared. So, if the diameter or the radius of the gauge is known, thickness of the material is known, and the material itself is known, its properties, the Young's modulus and the Poisson's ratio, then we directly have a formula which can give you the value of k prime, or I can use again a calibration procedure like what we discussed with respect to the board and gauge to calibrate the instrument, instead of looking at all these properties and then they are subject to their own errors and so on. We do not know exactly what these values are. We can actually calibrate the instrument instead of going through a formula like this. But the formula helps us in identifying the fact that there is a direct linear relationship between the displacement and the pressure. Therefore, in this particular transducer, we can say that pressure is converted to a displacement, and in fact this is called transducer action. We have of course come across similar things earlier. We talked about thermometers, the change in resistance is related to temperature. So, we measure the resistance change and then we infer the temperature change. Here we are finding out what the pressure is by measuring a displacement of a diaphragm element. The second one corresponds to what is called a bellows type gauge. In fact, we briefly referred to it earlier. In the bellows type gauge, we have actually a bellows which is very familiar to us. It is a tube with a accordion type shape. So, one side you have the pressure, outside you have the atmospheric pressure. So, if you introduce the pressure inside, this is going to compress. Of course, it is like a spring and it has a resistance to this motion. So, there will be some equilibrium when the spring force is exactly equal to the force due to the P minus Pa. Actually, you can look at the diaphragm gauge also the same way. The diaphragm is nothing but a spring, and the displacement is such that at the when the diaphragm has displaced itself from its original position to the changed position, the internal it is exerting a force exactly opposite to the force which is giving rise to that displacement. That is where it came to the equilibrium. Therefore, the element is actually a spring element, and what we have is simply pressure being measured by the spring constant of the system. Actually, if you remember, we use a spring balance for measuring weight. Actually, the same principle. The force due to the weight is balanced by the spring force, which is in the opposite direction. Therefore, the equilibrium position corresponds to the weight being equal to the spring force, and the spring force is proportional to the displacement of the spring multiplied by the spring constant, exactly the same. So, it is Hooke's law in action. And if you look at what we did just now in the diaphragm displacement is also according to Hooke's law. The material is undergoing a displacement by a Hooke's law kind of analysis, elastic deformation. Young's modulus has come into the picture only because of that. And in other words, to summarize the 2 or 3 different methods of measuring the pressure I have given now, they are all based on the same principle: the displacement and a spring, and then a force due to pressure which is balanced by the force of the spring, and that is what it is all about. So, the bellows type gauge also will undergo a displacement, and again I can say that the pressure is going to be related to a displacement, and therefore, you see that we have changed the original problem measuring the pressure to that of measuring the displacement. So, we have to, this is what we are measuring. We are going to measure displacement or the change in the position of some from some datum. You want to measure that change and then relate it to the pressure. So, the point is, the original problem of measuring the pressure has been now replaced by the measurement of displacement. So, what are the different ways of measuring the displacement? That is what we have to now look at it. So, if we are now thinking in terms of converting the pressure information to a displacement information, measuring the displacement information by using a suitable instrument or suitable transducer, and then working backwards and trying to find out what the pressure is. So, there are several ways of doing it. Actually, we can use a spring. One is to use a spring itself. Second one, we can measure the displacement by using a displacement measuring device. If the displacement is small, we need a very sensitive method of measurement, and usually the displacements are in fact small displacements. We will be able to see why the displacements are small, because in the case of the diaphragm, the displacement must not be such that it is going to give rise to plastic deformation. It should be operating all the time within the elastic limit. Okay? That is, elasticity is what gives rise to a spring, because once you remove the force, it goes back to its original position. So, elasticity means the displacement vanishes when the force is removed. When the force is brought back, it is going to displace. So, the displacement and the relation between displacement and force are 1 to 1. You remove the displacement or remove the force, there is no displacement. Okay? So, generally small displacements are required. Very small displacements cannot be measured by using a normal scale. Therefore, we have to devise some way of measuring this small displacement. So, what are the displacement measuring device? One is we can use a strain gauge. We can use a strain gauge. We can also use what is called an LVDT. This is a linear voltage differential transformer. It is a LVDT stand for the first letters of this. They stand for the first letters of these words here, linear voltage differential transformer. The strain gauge, in this case resistance change is measured. Electrical resistance of an element undergoes a change when it is subjected to a displacement, and therefore, what I am going to do is I am going to have one more transduction or one more transducer action. Pressure I am bringing rise to, I am giving rise to, pressure gives rise to a displacement. Displacement is now going to apply on an element which we call as a strain gauge, and this strain gauge element is going to undergo the same displacement, and because of this displacement the strain gauge is going to change its resistance. This change in resistance I am going to measure using electrical circuit. Therefore, we have a chain of transducer action here. We started with pressure, displacement to resistance change to some electrical change in electrical voltage or current. So, there is a chain of activity. In the case of LVDT, the displacement is going to be communicated to this differential transformer, and it is going to give an output which is expectedly or designed to be linearly dependent on the displacement. So, we will be very happy to have a linear relationship because it is easy to model, and therefore, LVDTs can be used for measuring very small displacement. A strain gauge can be used for measuring very small displacement. Strain gauges are also called as load cells. They are used actually for measuring stress in terms of the strain gives rise to stress gives rise to strain, and the strain gives rise to a change in the resistance, and the change in resistance gives rise to some change in voltage. So, you measure the stress. In this case, of course, pressure is the stress we are talking about. In the case of applications where strain gauge is used for measuring the displacement or the strain, in order to determine the stress, there is one area of activity where a strain gauge is used in elasticity, in study of stresses in structural members and so on. But in this particular example we are taking, we are interested in measuring a pressure using the strain gauge as the displacement transducer, which measures the displacement, or we can use the LVDT. It is a linear voltage differential transformer which can be used for measuring the displacement. What I will do now is to just to show this, because we have just enough time to look at this and take up the detailed study of these things in the next lecture. So, let us look at some of the things. I will come back to some of these in the next lecture. A strain gauge element. I said just a little while ago that we can measure the displacement using a strain gauge element. What is the strain gauge element? It consists of an electrical conductor, or it could be also a semiconductor. Nowadays, semiconductors are also used because they are much more sensitive than electrical than metal elements, and it is arranged in this form like this, what is shown here. Several lengths are going to, it is in this case you have a long length of wire twisted around like this, and you see that there is this is usually etched in on the backing material, which may be a plastic for example, and the resistance between these two ends is the resistance of this whole element depends on the strain, and in this case the strain direction or the active direction for this gauge is this particular direction. If this is subjected to a force in this direction, in the direction shown here, then the resistance will change and you will be able to get a change in resistance which can be measured in terms of change in voltage. We will see that in the next lecture of course. Or the differential transformer for displacement measurement. It consists essentially of a primary coil in the center, two secondary coils, one on the left and the other one on this side, and there is a core which is a ferrite core which is restrained or controlled by a spring force. There is a spring here, support spring, and in our case what I am going to do is the displacement I am going to get from my pressure transducer, I am going to communicate to this core, and this core will either move to the left or to the right and it will undergo a certain displacement. Suppose I give an AC alternating current to the primary coil, the two secondary coils are going to generate alternating current voltages, and if the ferrite core is moved to the left, there will be more coupling between the central coil and the secondary coil here, so that this will generate more voltage and this will generate less voltage. Okay. Suppose this moves to the right hand side, the secondary coil 2 will give you a higher voltage than the secondary coil 1, and if I connect these secondary coils back to back. Okay. So, if I measure, in other words, the difference in voltage generated by the secondary coil 1 and the secondary coil 2, that will be proportional to the movement or the displacement. Therefore, in the linear, that is why it is called the linear voltage differential transformer. Linear voltage, because if it moves to the right or to the left, the voltage which is developed by between the secondary coil 1 and secondary coil 2 in the differential mode, that is why differential transformer, that is proportional to the displacement. So, a linear relationship exists between the voltage. Of course, if secondary coil 1 generates more voltage, it will be in one direction, it will change the direction when this generates more. So, the variation of the voltage will depend on whether the secondary coil 2 is in a more intimate contact with the magnetic it is actually magnetic coupling. The magnetic coupling between the coil 1 and secondary coil 2 is determined by the position of the core. So, I think we will stop there, and in the next lecture what I am going to do is I am going to take up each one of these in some more detail, work out one or two examples to show or demonstrate how these particular instruments work, and then move on to a very important topic, that of measurement of unsteady pressure or time varying pressure, which is also very important from the viewpoint of applications. Thank you.